then resume record. Okay, so this is the final sort of practice paper. So obviously this, as I said, this is being recorded. I have to say that because I've just hit record. So the one that everyone got was the pyrometer. There's always a question where you're asked to identify the correct type of thermometer. There's sometimes more than one correct answer, but in this case, we're drawing lines to boxes, so it should be one answer per use. So the two that people got right, whoops, that wasn't it. We wanted the use of the pyrometer, which most people got the idea about measuring the temperature of a hot lava inside a volcano. All the other thermometers are probably not really appropriate due to their temperature range for measuring sort of very high temperatures. And most people got the idea about using a platinum wire, monitoring the resistance of the wire, and so it's you know, so that's fairly easy. But where we got it wrong, you need to think a little bit laterally. In an ideal world, you could use either thermometer for either of these two purposes. However, this one's mercury in glass. Mercury is poisonous, so we probably don't want to stick a mercury thermometer in your mouth, just in case it breaks. Okay, probably not the right one. Why did I draw a line? Because I was talking about it. So if I correct it, there we go. So it wasn't mercury in glass, it's measuring the temperature of melting wax. Because mercury thermometers are very precise, are very accurate, but they're not terribly good to put in your mouth. And a coloured liquid in glass thermometer, that would be what we'd actually measure the temperature at the inside of your mouth with. Now, where you get things wrong, it's obviously a good idea to use a pencil and a rubber, because then you can actually sort of erase it and correct it later. So the next question, now this one was quite well answered, so I'm not going to spend a huge amount of time on it, but there's a little bit of working that you can use to make your lives a little bit easier. So I'm going to show you that. So your first one is using the data from table 1. So you know in these exams, get like a data table, because it is geared towards people who want to do engineering. If you want to do any kind of engineering, or architecture, you need to be able to use data tables. So using data from table 1, estimate the melting point of gallium. So there's a whole sort of great big spiel here. What's it really saying? It's just saying that it's using a resistance thermometer, using a platinum wire thermometer, to measure the melting point of gallium, which is a metal which is solid at room temperature, but melts when it's in the palm of a person's hand. So using the data table from data 1, what we're doing is you're using the idea that the resistance when the gallium is melting minus the resistance of the wire at 0 degrees Celsius divided by the resistance at 100 degrees Celsius minus the resistance at 0 multiplied by 100. Then we substitute in our numbers. So the resistance of melting gallium is 13.3 minus resistance at 0 in pure melting ice, that would be 12.3, divided by resistance in boiling water. Well, we say that would be 100, 15.7, and then the resistance in pure melting ice would be 12.3. Multiply it by 100, and we end up with, well, about 29. So it's 29 degrees Celsius. Okay. So there's our answer. And is that consistent? Well, it says that it melts when it's placed in the palm of a person's hand. Well, your body temperature is about 37 degrees Celsius. So yeah, that would be about right. So then we get another one where they do the same experiment again, but this time they're using a thermistor. So we're trying to use a thermistor here. So we do exactly the same formula, but it's asking me to explain why it's different. So we're expecting an answer that's not 29 degrees Celsius. When we're looking at why it's different. So the data from table 2, so we're using the idea that it's the resistance of the gallium minus the resistance at 0 divided by the resistance at 100 minus the resistance at 0 times 100. Substitute in the numbers. Well, the resistance of the gallium is 31.3 minus the resistance at 0, which is 47.0, divided by the resistance of boiling water, that boiling water 16.5, minus resistance at 0, which is 47.0. Okay. So, have we got that right? Yeah, that looks about right. Multiply it by 100. So, have I got that right? No, I haven't, because I want the resistance in pure melting ice, and that's, yeah, no, that is correct. So we get a simple calculation, 31.3 minus 47 equals minus 15.7 divided by 16.5 minus 47 gives you minus 30.5. Doesn't matter that it's negative, because it just gives you a final answer, because the two negatives will cancel each other out. So 15.7 divided by 30.5 gives you 51, multiplied by 100 gives you 51.475 or whatever. Well, we say 51 degrees Celsius. So if it's 51 degrees Celsius, we notice that that is way off. That wouldn't melt in the palm of your hand for a start. So which one's likely to be wrong? Well, it's likely to be the thermistor. Obviously, we're using the wrong bit of physics for the thermistor. And so why is it not right? Well, it's all to do with the fact that the resistance of the thermistor does not vary linearly. Okay, and that then takes you to your that then sort of takes you to your second mark. How do we know this? Well, we know that this formula relies on a linear relationship between any property and temperature. We know because we can see here that this is clearly wrong. So that must not be working properly. If that doesn't work properly, it's because it's not a linear relationship. Resistance does not vary linearly with temperature. So on to the next one. So we know this is a graph question, and I'm going to dwell on this one because this is one that a lot of people struggled with. So we start off with a Boyle's law experiment. You've got a pressure gauge, you've got a fixed mass of gas, the graduated scale to read the volume, got some kind of weird screw thing here. And so we know it's most likely to be Boyle's law. You'll always get a graph question based on a gas law in unit 3. So state Boyle's law. Well, we know we've got to think about the exact sort of law. It's a simple law. It's for a fixed amount of an ideal gas at constant temperature the pressure of the gas is inversely proportional to its volume. And that's basically it. We know it's 2 marks, so we do need to put the idea it's a fixed amount, constant temperature, and the fact that it's an ideal gas. If it's not an ideal gas, it won't obey Boyle's law. That's one of the definitions of an ideal gas. So then to state 2 quantities which a student would have needed to keep the same throughout the experiment. I think most people got it, although we need to be careful about wording. It's the amount of gas. I accept mass. I accept the mass of the gas, but really it's the amount, the number of moles, and the temperature of the gas. Okay, and that's how you do part B. Most people who attempted got at least 1 out of 2 correct in that one. Now, So that the second bit is the table question, and it's a simple calculation, but there's a little trick you can do here. I'm going to show you a little trick. When you're drawing the graph, you want all your numbers to be multiplied by 10 to the same power. So if you look carefully, you've got 0.6 times 10 to the power of minus 5. Well, that's going to give you a number times 10 to the power of minus 6, a single digit times 10 to the power of minus 6. Here, we're going to get it's a largish amount. So, sorry, you're going to get double digit times 10 to the power of minus 6. Here you get a single digit times 10 to the power of minus 6. So if we keep it all times 10 to the power of minus 6, it makes life a lot easier. Because 0.6 times 10 to the power of 5, 1 over that is 16.7. Okay. Now we want appropriate number of significant figures. Here we've got one significant figure, maybe 2, and here we've got 3. So really and truly, I need to put my answer to 2 significant figures. In this case, you would allow 3, but really we should say it's 17. Should be 17. So every single one here is to I'm going to do to 2 significant figures. So we'd say 2.4 times 10 to the minus 6. 1 over 1.9 is 5.3 times 10 to the minus 6. 7.7. 10. 14. Oops, sorry, that should be 13, sorry. Because that comes out to be 12.5. And 1 over 0.7 is 14. Okay. So that's the correct way. Now, if you did that to 3 significant figures, you actually would still get the mark. If you did 4 or 5 significant figures, or you did 1 significant figure, it might start to be a bit questionable. Okay. Then it says, so I've calculated that, and I've used the correct number of significant figures. So it's 1 mark for calculation, 1 mark if significant figures are correct. Then you're plotting a graph of volume on the y-axis versus pressure on the x-axis on the graph paper, and provide a line of best fit. Now remember, when you're doing the real exam, if you're doing it on site, that's great, you get the exam paper. If you're doing it at home, my advice is to print the exam paper out if you can. If you cannot, you need some graph paper. Now I have sent people graph paper. If you need me to send you an electronic piece of graph paper so you can print it out at home, you can do so. So if I plot my graph on the other side, on my other piece of paper here, I've got to first of all establish a scale as per normal. So I'm just going to zoom out a tiny bit there. So you've got the paper. So we know that our value is going to go from our value of volume on the y-axis, so the volume goes on the y-axis, it's going to go from about 1 to 7. So if I start it at 0, 1, 2, 3, 4, 5, 6, 7, that's pretty much spot on. So that's what I'm going to use. So my volume, now I've got to label my axis carefully. It's volume of air, and it's times 10 to the power minus 5. So it's volume in meters cubed times 10 to the power of minus 5. Okay, I'm going to put that up there so I don't have to put it on the axis here. It makes it easier. It makes it easier to draw. So 0, 1, 2, 3, 4, 5, 6, 7. Okay, I don't go above 7, I don't think. Let's just double check. No, my highest value is 7. Lowest value is 1. Well, it's pretty close to 0. So we put the origin on. And then you have pressure to the minus 1 on the x-axis. Now this is a little bit more difficult because we go from pretty much 0 up to 17. So if I try to go in 2s, it'd be 0, 2, 4, 6, 8, 10, 12. Even if I started at 2, 4, 6, 8, 10, 12, 14, it wouldn't fit. So I've got to think a little bit more carefully about how I actually organize my axes. Well, what I'm probably going to have to do is if I start at 0, I'm probably going to have to go up in where 2 squares is 5. It's not my favorite scale. It's a little bit more complex to plot, but that's the best way because that goes up to 15 there. So 14 is about here. So we've got, so our highest value, sorry, the highest value is 17, isn't it? So we have 16. And 17 is just off the end here, isn't it? Is that right? Yes, just off. It's just at the very, very end. I think we can just about get away with that. So we probably want to make it easier to plot. So we're going to go up in 1. So it's 1, 2, 3, 4, 5. 1, 2, whoops, 2 there, not there. 3, 4, 5. 1, 2, 3, 4, 5. Then we go 1, 2, 3, 4. 17's there. Okay, so that just about fits. So that's pressure to the -1 in pascals to the -1. Okay, and we know that's going to be times 10 to the power -6. Okay, that just makes it easier to plot, makes it a lot more straightforward to plot. So then we're just plotting. So all we really need to do, I'll do this live so you can see it. So where the volume of 1, we know that the pressure to the -1 is 2.4 times 10 to the -6. So that's 2. Well, 2.5 is there, so it'll be just before that. 2.4, about there, I reckon. As long as you're within about 1 small square, it's acceptable. So at 2, it's 5.3, so 5. Well, that's 5.25 there, so it'll be 5.3, it'll be a little bit further along. Next one is 7.7, so there's 3, there's 7 there. 7.25, 7.5, 7.75, 7.7 is just a fraction before it. The next one is at 4, and that'll be 10. Okay, so you're just plotting very, very carefully. 5 is at 13, so that's 10. Let's see, that's 11, 12, 13 there. And at 40, and the next one's at 6, which is 14 exactly. So 14, well, that's 15, so that's 1, 2, 3, 4 makes 14. And the last one is at 17, which is just at the very end there. Okay, so I've made maximum use of my graph paper. It's not perfect, but it'll do. Now, the thing to remember here is when you draw your line of best fit, it's a single straight line. And it should have roughly the same number of points below the line as above it. Okay, even if I know we're expecting it to go through the origin, but in this case, it doesn't quite, okay? So then we're looking at convenient, so then that's the graph drawn. So the next part then says, explain whether or not this proves Boyle's law. Now, Boyle's law says that pressure times volume is a constant for a fixed amount of gas. So volume divided by pressure to the -1 should also be a constant. Okay, because it's got pressure to the -1 on the x-axis. So what we need are 3 corresponding values for volume divided by pressure to the -1. So what I need to do is take 1 at the bottom here. Now remember, this is a bit of an investment because you can bet your bottom dollar you'll have to measure a gradient. So this is a nice convenient point here to read, nice and easy. So that's 0.8 and that's 2.5. We'll measure 1 up here somewhere. We'll find a nice convenient one. That looks like a nice one at 15 there. So that would be 6.2. Okay, and we pick one in the middle just for good form. So I'll pick one maybe about there, I think. Always draw your construction lines. Very important to draw construction lines when you're measuring values from a graph. So it's 5, 6, 7, 8, 8.5, and 3.1, 2, 3, 4. So we're going to ignore the powers. Why? Because you don't need them here, just for a moment. So start off with our low value, which would be 0.8 over 2.5. The next one would be 3.4 over 8.5. And the last one would be 6.2 divided by 15. What we've got to do then is just calculate it. Remember, we're not looking for identical values. You're looking for values of the right sort of order of magnitude. .41. Well, I'm not happy with that. They're not the same. So values vary. Values of pressure times volume vary. So it's not proven. Now here you can actually, if your graph proves a particular law, then you can say it's proven. If your graph doesn't prove it, then you say it's not proven. The fact that it's proven or not proven is not dependent on a finite sort of final answer. The fact that it's proven or not proven actually depends upon your reasoning. So even if you just use the basic rule of whether or not it's a straight line through the origin, you said it's a straight line that approximately goes through the origin, then yeah, you'd get away with that. It's not about what the answer is here. It's about the reason for the answer. So what we have is an answer. So what we have is an answer that's consistent with a reason. If you just say proven or not proven, it's not enough to get the marks. You have to have some sort of consistent answer there. So the alternative answer is to say whether or not you think it's a straight line through the origin. Okay, so that's something you have to remember. Now, as we continue on, we're then given the question to measure the gradient. You know you always get a question on measuring a gradient, which is why I nag so much about measuring gradients in practical work. So if we look at the graph, we measure the gradient. Well, there's no point in reinventing the wheel. You've got some convenient points at the top and bottom of your line here already. Obviously, if you haven't proven whether or not it's proportional, then you need to find your convenient points and draw your triangle. But here you can see that those values make a nice, convenient big triangle. We're looking for a convenient big triangle, easy to read. So we know y1 is 6.2. We know that x1 is 15. We know that x2 is 2.5 and y2 is 0.8. So when you're measuring your gradient, you quote your values first. You start with your working. y1 minus y2 over x1 minus x2. You can say it's y2 minus y. Sorry, you can say it's y2 minus y1 over x2 minus x1. You can do it that way around if you wish. It all comes out in the wash and all sort of makes for the same answer anyway. So as we're doing that, we're looking at our values. So y1 is 6.2, y2 is 0.8. So 6.2 minus 0.8. Very important to actually quote your values. One of the things I'm looking for, remember, I'm not looking for a specific value for your gradient. I'm looking for the technique that you've used to actually measure it. So x1 minus x2, that's 15 minus 2.5. So you should show your stages of working. So 6.2 minus 0.8 gives you 5.4. Divided by 15 minus 12, 2.5, so that's 12.5. Now, Now we've got to think about the powers. So the power on the y is 10 to the minus 5. The power on the x is 10 to the power minus 6. You've got to put them back on there, okay? Very important. Otherwise, the graph, simply put, your the graph won't, you know, the gradient will be incorrect. So, if we measure it, okay, well that's just going to be that cancels out to be 10. So we have 5.4 divided by 12.5. Because I've had to do this from scratch, I have to do the calculation. Makes, oops, let's try again. 5.4 divided by 12.5 equals 0.432. So multiply it by 10, we end up with 4.32. Okay, now that's worth 2 marks. 1 mark is for correct reading from the graph. 1 mark is for, sorry, one mark is for correctly drawing a triangle on your graph. Another mark is for correct reading and calculation of your gradient. 3rd mark is for the correct unit. So it's the units of y divided by the units of x. So on the y-axis, we've got meters cubed. On the x-axis, we've got pascals to the minus 1. So it's meters cubed divided by pascals to the minus 1. It's the same thing as saying meters cubed pascals, or pascals meters cubed, doesn't matter which way around you do it. Okay, that's it. Job's done. Always, when you get a final answer, double underline it. By the way, if you are working on separate paper in the real exam because you can't print out your exam paper, fully understandable, please, please, please put your question number. Please put your question number on there so that it's really clear which question you're answering. When I was looking at some of the scripts that were handed in to me yesterday and today, what I saw was some of the questions didn't have the question number, so it's really hard to tell where your answer was, and there may have been some lost marks from that, I don't know, because I can't tell. Right, so we've got, then use your answer to see part 4, so it's this answer, use this answer to calculate the number of moles of gas in the cylinder. Well, we haven't got to rearrange it. Y equals mx. You could say plus c, but it's y equals mx. So if that volume's on the y-axis, 1 over pressures on the x-axis, volume's on the y-axis, 1 over pressures on the x-axis. So that bit must be the gradient. Remember, when you come to do the real exam, you might not get it in the y equals mx plus c format. So you might have to remember to rearrange it. So you make whatever's on the y-axis the subject. You then separate out whatever's in the x-axis. Okay. So, for example, and I'm going away from the answer now. I'm just going to show you. Imagine you drew a graph of temperature versus volume. You'd have to rearrange that to make temperature the subject. So that would be T equals PV over RT. And then as you change the volume, then you need to separate out the volume. So it's T equals P over RT, over RT times the volume. Should be NR, not RT, I do apologize. NR times the volume. Okay, and then you say Y equals MX. And whatever that bit is there, that should be constant. That's going to be your gradient. Okay, back to the question. Here we've got it in a nice convenient format. You might not get it in a nice convenient format in the real exam. That's the way it goes. So if that's the gradient, you say so. The gradient is nRT. And I want to calculate the number of moles of gas. So I want to find N. So N is the gradient over RT. So the gradient, so we substitute it in, 4.32 over 8.31 times, what's the temperature? There's the temperature, it's 300. So we end up with 4.32 divided by 8.31 divided by 300 gives you 0.001 0, 0, 1. Well, I think I go to 3 significant figures, I suppose, here. 173 moles. And because that's my final answer, I double underline it. Okay. It then says, suggest and explain whether the measurement of volume or pressure contributed the most to any random errors in this experiment. So you've got to stop and think a little bit here. If you look at these values, all of the values of volume are to 2 significant figures. So are some of the values of pressure, but some of these are down to 1 significant figure. If they're down to 1 significant figure, then you've got a much larger potential uncertainty. So pressure had the largest uncertainty. As some values were only to 1. You can use the abbreviation here, 1 significant figure, okay? Because if you think about it, that means the uncertainty would be well over, if it's down to 1 significant figure, the uncertainty in a particular value is about 10%, which is not very good. Okay, we're trying to aim for a minimum, for a maximum uncertainty of about 5% in physics experiments. Okay, so that's how you do that graphing question. It's really important to get that, you know, to get that right. It's easy marks. It's very easy money. So all you've really got to do is remember to manipulate the values in the table. You'll have to draw a graph. If you get your scale wrong, don't panic. It's only 1 mark. Okay, draw your graph. Even if your graph is awful and you're struggling to draw the graph, if you just draw a straight line and measure its gradient, you get error carried forward marks on here. As long as you show your big triangle and you correctly measure its gradient, as long as it's clear exactly what you use. So if you put an axis together, but you didn't plot the points, you just drew a straight line, you measured its gradient, you'd still get these marks. The error carries forward at every stage. So if you can do this, if you can't measure a gradient, but you could do this bit, then do this bit with a made up number for the gradient. For the simple reason that the error carries forward. If I'm not looking, remember, for the correct answer because I already know what that is. What I'm looking for is, can you do what's needed at each stage? If you can't do that stage, make something up so that you can show that you can do something at this stage. It's very, very important with structured questions. I'm looking for working. Errors always carry forward. Right, on to question 3. So you know this is going to be gas laws again, but this time we'll be looking at some molecular kinetic theory with it. By the way, tomorrow's lesson, unless people ask otherwise, I'll be doing a derivation of PV is equal to 1/3 NMC squared, because I think that that's one area that I think I need to really sort of talk you through, because I gave you that on Seneca, and I don't think everyone fully understood it. Right, so you've got a tank in a picture of a diver. You're told the pressure, megapascals. So that's 2 times 10 to the power of 7 pascals, because it's 20 million pascals. Temperature 200 degrees Celsius. You know if it's going to be gas laws. 273 plus 20 is 293 Kelvin. And you're given the volume, that's okay. Okay? So you want to first of all show there are 80 moles of air in the tanks, okay, in the tank. The way we do that is we just use the equation of state. PV is equal to nRT. N equals PV over RT. Substitute 2 times 10 to the power 7 multiplied by 10 to the power minus 2, because that's just 1 there. Divided by the molar gas constant. It's on your formula sheet. And so you can then just plug in the numbers and you get 82 moles. And it says show that it's approximately 80. So you need to include the final step to show that is approximately 80 moles. Okay? That little that double squiggle there, that means approximately equal to. Okay? Now for the next question, you can either use your calculated value of 82, or you could use 80. It's the working, it's the correct use of working that I want to see, not just the answer. So then asks you to calculate the number of molecules. Well, to work out the number of molecules, it's the number of moles multiplied by Avogadro's number. Again, Avogadro's number is on your formula sheet. So it's 82, well, what comes as 82.1 multiplied by Avogadro's constant, which is 6.02 times 10 to the power of 23. And we get 4.94 times 10 to the power of 25 particles. And as it's my final answer, I'm going to double underline it so that it's really clear that that's what my answer is, because I'm looking for the answer as well. Then you've got the molar gas constant of air is 0.029 kilograms per mole. So we end up with, want to work out the mass of one molecule of air. So the mass of one molecule of air, well, it's going to be the number of, mass of one molecule of air is going to be mass of one mole, which is 0.029 divided by 6.02 times 10 to the power of 23. So we work it out. That's 0.0048, 0.0048 times 10 to the power minus 23, which is 4.8 times 10 to the power of minus 26 kilograms. Okay. You then calculate the kinetic energy of one molecule of gas. So the kinetic energy of one molecule of gas for one particle is 3/2 kT. Beware, some people, when they handed it in, there might have been just something to do with a misprint somewhere, but you said 32 kT. It's not 32, it's 3/2. It's 3 divided by 2. So that's going to be 3/2 times Boltzmann constant, which again is on your formula sheet. That's 1.38 times 10 to the power minus 23 multiplied by 293 Kelvin gives you 6.07 times 10 to the power minus 21 joules. Okay, we're expecting a tiny amount of energy. It then says, hence calculate the total internal energy of the gas in the cylinder. So the total internal energy of the gas in the cylinder is multiplying the whole number by the number of molecules. So even if you really couldn't do that bit, if you wrote a sensible number down and multiplied it by Avogadro's constant, hang on, multiplied by the number of molecules in the cylinder, sorry, multiplied it by the number of molecules, which was on the previous page, 4.94 times 10 to the 25. Should give you about 3.0 times 10 to the power of 5 joules. Okay, that's the total internal energy. Okay, we need through that question. Remember this question, the third question, the gas laws questions are the longest ones. This says calculate the root mean square speed of an air molecule in the tank. Now there are lots of different ways of doing this. Possibly the easiest way of doing it, if we know the number of molecules and we know the mass of each particle, we can actually apply it into PV is equal to 1/3 nm times the mean square speed. So we know the number of molecules, so it's 1/3 multiplied by the number of molecules. Well, where do we get that? That's over here, 4.94 times 10 to the power 25. multiplied by the mass of one molecule, 4.8 times 10 to the minus 26, multiplied by the mean square speed. Okay, so we've got to think carefully. We've got to think carefully. Well, we're going to have to rearrange that. So we've got pressure times the volume. So the pressure it told you was 2 times 10 to the power of 7 pascals, multiplied by 10 to the minus 2 over this whole sort of shebang here, this whole sort of formula here. So 1 over a third is simply 3 times it. Then you've got 4.94 times 10 to the power of 25 times 4.8 times 10 to the power minus 26. Okay, so you calculate that and you end up with 252,101. But remember, that's the mean square speed, and it wants the root mean square speed. Be very careful as to whether or not the question is asking for the mean square speed or the root mean square speed. So we need to square root it. So the square root of 225,101 gives you 502 meters per second. Okay, and that's a reasonable value for the mean square speed of a particle of gas at room temperature. It's going to be of the order of hundreds of meters per second. Right, on to the next bit. It then says the cylinders are fitted with regulator valves. I've got to read this bit carefully, which release the compressed air at a pressure similar to the surrounding pressure. So the pressure at the surface of the water is 10 to the power 5 pascals. The pressure 30 meters below the surface is 2.9 times 10 to the power 5 pascals. Assume the temperature of the water is still 20 degrees Celsius. We know that we've got to say that's 293 Kelvin. Okay, always well worth noting that. You're then given that the average volume of a diver's lungs is 6 times 10 to the minus 3, calculate the number of full breaths a diver can take when on the surface of the water before the air in the tank runs out. So you want to calculate the volume on the surface. Now, we're assuming here we're still at the same temperature the whole time. Okay, so the temperature of the water, therefore the temperature of the gas in the water, the gas in the cylinder, and therefore the temperature of anything is going to be 293 Kelvin. So we use Boyle's law. Okay, so the volume at the surface equals the pressure at the surface is going to be a constant. So that's going to be equal to the volume in the cylinder multiplied by the pressure in the cylinder. And we want to work out the volume at the surface. So the volume at the surface is going to be the volume in the cylinder times the pressure in the cylinder divided by the pressure at the surface. So the volume is 10 to the minus 2, but the pressure in the cylinder was still 20 megapascals. Divided by the pressure at the surface, well, that's 1.0 times 10 to the power of 5. And so we're expecting something like 2.0 meters cubed. That's the volume at the surface. So that's the total volume of air once you've actually released it. So if that air is used to fill the diver's lungs, we know that that's the volume of one breath. So the volume of one. So we want to work out the number of breaths. I'm going to give that capital N with a little B underneath it, so I'm not mistaking it for anything else. Well, the number of breaths times the volume of the lungs is going to be equal to the total volume at the surface. So the number of breaths is going to be the volume at the surface divided by the volume of the lungs. So that's 2 divided by the volume of the lungs, which is 6 times 10 to the minus 3. Okay. And it comes out to be 333 breaths. You can round it off to two significant figures if you like, but the number we're looking for should be about 330 or 333. Okay, and that does the job. That's it. So the key bit here was applying Boyle's law to work out the volume of the air at the, when it's released to the surface, and then realizing that that will go into small chunks of 6 times 10 to the minus 3 cubic meters into the diver's lungs. So it will go into the diver's lungs 333 times, which does not mean you get to spend a lot of time underwater. That's just at the surface. Now it says the diver dives to a depth of 30 meters. How many breaths can they now take from a full tank at this depth? So here it's the same question, but it's different value for the pressure. It's 2.9 times 10 to the power 5. So we use exactly the same idea. So the volume of the air underwater times the pressure underwater equals the volume in the cylinder times the pressure in the cylinder. So we want to work out the volume underwater again. It's exactly the same. So I'm going to put that down here, I think, because I'm not going to have enough room there. So the pressure in the cylinder, remember, is 20 megapascals. Volume of the cylinder was 10 to the minus 2 cubic meters, divided by the pressure under the water, which is given here, 2.9 times 10 to the power 5. And it comes out to be about 115 breaths. Okay, so that's only worth 1 mark because they're basically doing the same thing again. However, the next part is an application question. So it says, explain why the divers have to take the depth of their dive into consideration when planning a dive. Well, we know that the deeper you go, the fewer breaths you can take. So that's the bit that's obvious from the data. So that's the first bit. So the deeper dives result in fewer breaths available. So the diver needs to, well, the simplest answer is to say that they dive for a shorter time. For deep dives, you could say that we'll have extra tanks of air. Okay, and that's what divers have to do. As part of if you want to qualify in this country as a diver, it's what they call a PADI qualification. You have to be able to work out how long you've got before you have to go back up to the surface again, because you can't just go to the surface straight up to the surface, because all the dissolved gas in your blood starts to sort of escape, and you end up with bubbles of air in your bloodstream, which is not very healthy for you. It's called the bends. So you have to be able to know how long you've got before you have to get back up to the surface. So if, as part of your PADI qualification, if you want to do scuba diving, you're actually taught how to work that out, and you have a little indicator, like, oh yeah, it looks like a wristwatch, that tells you how much air you've got left, and therefore you can work out how long you can spend continuing your dive. It's very important. The reason why the PADI qualification exists is actually to make sure that people don't kill themselves while they're scuba diving. Anyway, let's move on. So we're nearly there. It's a very long question. It's about a third of the paper, this question. So faulty tanks can explode, causing the air to expand rapidly. Calculate the volume the full tank of air would occupy at atmospheric pressure and room temperature, 293 degrees Kelvin. Well, actually, it's exactly the same as the previous answer, because here at the surface, that is the atmospheric pressure. So it would be 2 cubic meters. It's a simple answer. Now, if you want it, you could work it out using Boyle's law. But I would say you can do these questions by inspection. This one you can do by inspection because you recognize that it's the same pressure. So we would say, it's the same pressure as C part 1 as C part 1, which implies same volume. Okay, if you're going to use inspection to get an answer, i.e. the answers obviously think you've calculated it already, you need to say where you get it from, just in case you make a silly mistake. Because if you actually write down the wrong number here or something like that, if you've used the correct physics, you get 1 mark at least. Then says if we assume that the expansion of air is isobaric. Now, isobaric, remember, means we're not adding thermal energy to the gas itself. At 1.0 times 10 to the power of 5 pascals, how much work would the air from the cylinder do on the atmosphere as it expands rapidly to the volume calculated in D part 1? So we know that if it's isobaric, the work done is pressure times the change in volume. So if you've got a pressure, we know that the pressure is 10 to the power of 5 pascals multiplied by the change in volume. Well, the change in volume is going to be the final volume minus the initial volume, which on the question was 10 to the power minus 2. So that would be 1.99, okay? That's 2 minus 0.01. So 1.99, it doesn't make a huge amount of difference if you use 2. So we end up with the work done is 1.99 times 10 to the power of 5 joules of work. Okay, it's quite a lot. And that's why exploding air tanks can be very dangerous. Right, so then says use the first law of thermodynamics to describe and explain what would happen to the temperature of the air as it expands rapidly. So we know we're looking for the change in the internal energy of the gas is equal to the thermal energy supplied plus the work done. Now it's the work done on the gas. Okay, so we know if it's adiabatic. So it's isobaric. If it's isobaric, we're going to assume that if it's done rapidly, it's probably going to be it's going to be probably not really going to be adding any thermal energy to it. So we know that the work done would be negative. Okay. So if the work done's negative, you can assume that the change in internal energy is negative. Why? Because work is done by the gas. Remember, when gases expand rapidly, they cool down. Okay? Work is done by the gas, therefore the temperature falls. Even if you just said the temperature falls because work is done by the gas, or the work done on the gas is negative, that would get you your 2 marks, okay? But this is, remember, the first law of thermodynamics. So it's always well worth quoting it, because if you get into a complete muddle, if I can see you've used it, you've made an attempt at using it, you can sometimes still get that 1 mark, that one compensation mark. Right, the next question is always going to be a latent heat and specific heat capacity question. Okay, so you've got, again, a table of data here, and it says the boiler, there's a boiler used to heat water. One method is heating water in a central heating boiler, which burns natural gas to provide thermal energy. In other words, it provides energy at a constant rate. Figure 2 is a picture of a central heating boiler. The boiler heats 0.2 kilograms of water per second from 20 to 50 degrees Celsius. So calculate the energy required to heat up the water. So even if you read through that question and it gave the screaming abdabs, doesn't matter. The question here just wants the energy and change in temperature. So you know the change in temperature is from 20 to 50, so that's 30 Kelvin. So it's N mass times specific heat capacity times by the change in temperature, which we then substitute. Well, the mass is 0.2. Specific heat capacity is in the top of the question here, 4,200. We don't have to convert any units here. Change in temperature was 30 Kelvin. I'm not going to bother with the Kelvin bit. It's more trouble than it's worth. Okay. And so we end up with a sensible answer. And a sensible answer is 25200. Is that right? Check it. Oops. 0.2 times 4,200 times 30. Yep, 25200. So that would be 25200 joules. That's the correct answer. And we're going to put it down here just for form's sake. Okay, so that's the energy supplied to heat up the water. The question now, this next question I'm going to dwell on because a lot of people missed a point here. It says hence. Hence means using what you've just worked out. State means you don't really have to do any kind of calculation. Or if it is a calculation, it's an incredibly simple one. State the power output of the boiler. So using the previous answer, somewhere in the previous answer, it'll give you the power output. Well, that's the energy required to heat the water, okay? And it tells you it heats up that amount of water in 1 second. That's per second. So if that's per second, we know that's going to be, well, power is energy over time, and the time is 1 second, okay? So the energy is basically 25200 divided by 1, which is 25200 watts, okay? As long as you just quoted that number, you got the mark. It's that easy. So I'm moving on. Some new boilers use water vapor created by burning gas to reduce wasted energy, causing it to condense on the water pipes before the water is heated by the boiler. The mass of water vapor condensing into water is 0.05 kilograms per minute. Now, careful. We don't like minutes in physics, not really. But what we could do here is to say, well, okay, stop and think. We could actually, it looks like a really difficult thing, a really difficult sort of passage to understand here. But what we're really after, the important bit, is the idea that water vapor is turning back to a liquid, and that amount is turning back into a liquid every minute. So it then says, calculate the energy given up by 0.05 of water vapor as it condenses back into water. We're assuming here no change in temperature. Is that a correct assumption to make? Not entirely sure, but it'll do. So if we're assuming that there's no change in temperature, we're saying that the energy is mass times the specific latent heat of vaporization, which is on the last bit here. Specific latent heat of vaporization is 2.26 times 10 to the power 6 joules per kilogram. So the mass is 0.05 multiplied by 2.26 times 10 to the power of 6. And we end up with 11300 joules. Okay, it's just plug it into your calculator. It's pretty straightforward. There's your answer. Okay, so the actual question looks complicated, but it's not that complicated. So as we then move on, it says calculate the power output of the condensing water vapor. In other words, if that's the energy and that's the time, 1 minute, so T is 60 seconds. So the power is the energy transferred divided by the time. The energy transferred is the same as before. Again, if you get this bit wrong, as long as you show that you use this value over here, you still get the marks. Divide it by the time taken, which is 60 seconds. Again, got to be careful here. When you see times in minutes and so on, it should raise a little alarm bell. Even if you don't have to convert it in the end, it should raise a little alarm bell that maybe you might have to. So we do our calculation and we end up with 1880 watts. Okay, that's the answer. Okay. So it then says, what percentage of the total power output of the boiler is provided by condensing water vapor? So if we think about it, we looked at the power sort of output here, is at the top here, 25200. And we know that amount of the power, is coming from the condensing water vapor. So it's literally an efficiency calculation. Well, it's more or less an efficiency calculation. We've just got to remember it's going to be 1880 divided by 252000, and that comes out to be 0.747 and some other bits. So we could say multiply that by 0.07. I apologize. So we multiply that by 100 to get it to percentage, and we put it to the nearest percent. It would be 0.5%, let's say, 0.1%, 7.5%. Okay, if you said 7%, it would be acceptable only if you showed this calculation. Okay, which is about right. Most condensing boiler manufacturers claim 5 to 10% of the energy is recovered from the condensing steam. It then says an alternative method of heating is used to use storage heaters which contain concrete. The concrete is heated to 80 degrees Celsius overnight and release energy at a constant rate when not being heated. Because electricity is cheaper at night in some houses than it is during the day. They have what's called an economy 7 meter, which means because people don't use much electricity at night, the electricity can sometimes be a bit cheaper. So it says calculate the energy transferred as a storage heater containing 50 kilograms of concrete cools from 80 to 20 degrees Celsius over 16 hours. So again, this looks like a big sort of application, really, really confusing. But when you read the question, what's it really asking? It wants the energy for a change in temperature and a mass. So we know that's going to be MC times the change in temperature. The change in temperature is from 80 to 20, so that's going to be minus 60 Kelvin. It's going to go down. We know the mass is 50. We just don't know the specific heat capacity of the concrete because it tells you it's concrete. So if you go back to the beginning of the question, it tells you the specific heat capacity of concrete is 1000 joules per kilogram per Kelvin. Okay, so then we just want to say that E equals M, the mass, which is 50 kilograms, multiplied by 1000, multiplied by minus 60. We got 3 million. So that's going to be, well, the energy transferred, it doesn't want to know whether it's positive or negative. It should be minus 3 million. Joules. So if you just said 3 million, I didn't mind at all. Or you could say it's 3 times 10 to the power of 8 joules or 3 megajoules. Any of those answers would do the job nicely. What I'm after when I'm marking papers, I'm after the use of the correct formula and correct substitution with the correct calculation. If you miss out a minus sign, unless a question really seemed to be implying that you needed to put it in, I usually forgive it. It then says, calculate the average power output of the heater over 16 hours. So it's 3 million joules over 16 hours. So the power is energy over time. Whoops. So the energy is 3 times 10 to the power of 6. That's the same number as that, divided by the time of 16 hours. So it's 16 times by, well, if you want to work out how many seconds are in an hour, it's 60 seconds to a minute, multiplied by 60 minutes to an hour is 3,600. Now, whether you say it's 60 times 60 or 3,600 is neither here nor there. It doesn't really matter. But you get the final answer. The average power comes out to be, pick up my notes, there we are, comes out to be 52 watts, which isn't very powerful. Okay, so that then tells you the average power output. So that is your question 4. Question 5 is always on the linear coefficient of expansion. So you've got steel rail tracks made in 20-meter lengths. They're bolted together when laid to make a railway. You've got a picture of what that looks like and the idea that there is a gap in the middle here. We know it's a thermal expansion question. You're told the linear thermal expansion coefficient of steel is 1.2 times 10 to the power minus 5, Kelvin to the minus 1. So you have to calculate the change in length over 20 meters. So you know that the change in length is equal to the length, which is 20 meters, multiplied by the coefficient of expansion, multiplied by the change in temperature. So for 10 Kelvin, that's 10. And so we end up with 0.0024 meters. Okay, there's your final answer. Very easy, 2 marks if you know your formula. So if that's the case, then we know that for every 10 Kelvin temperature increase, the track will expand by, well, about 2.4 millimeters, which is about right. It then says a railway track is laid when the temperature is 10 degrees Celsius. In the UK, the temperature is not expected to rise above 30 degrees Celsius. So how much gap would they put in between the lengths of rail track? Well, if it's laid at 10 degrees Celsius and it's at 30, then you're going to need twice the gap. We know it would expand twice the amount. It would expand twice the amount. Okay. So if it expand twice the amount, we know it's twice the expansion. You could actually just plug it straight into that formula and say 20 meters times 1.2 times 20 Kelvin. But the answer comes out to be the same. You know that you should put about a 5 mil gap because it would come out to be 0.0048 meters. Okay, that then gives you a final answer. Okay, so that would give you the answer to either by inspection, so knowing it's 2 times the expansion of 10 Kelvin because that's 20 Kelvin, because it's going from 10 to 30, or by plugging straight into the formula. It doesn't matter which way you do that. Now the next question tripped a lot of people up. That's because it is a teeny bit more complex. So it says, on a really hot day, the track reached the temperature of 40 degrees Celsius. So this would imply that it goes to 40 degrees Celsius, 10 Kelvin above 30. Now, you've got to think carefully. Calculate the expansion of 10 kilometers of track allowing for the gaps calculated in part B. So with the gaps, So with the gaps, you'd only have a no gap at 30 Kelvin, sorry, 30 degrees Celsius. You only have no gap at 30 degrees Celsius. So the change in temperature there is again 10 Kelvin. Okay, so you have to think a little bit laterally here. So that's when you've got the gaps, but then it will continue to expand. The whole track will then start to expand beyond that. So if that's the case, we know that the expansion for every 10 Kelvin would be 0. Now I've got to get my notes. My notes have got a little bit disjointed. Bear with me for a second while I find it. Be 0.0024 meters per 20 meter track, but here you've got 10 kilometers of track. So it's 10,000 meters of track. I could put it up here, couldn't I? 10,000 meters of track divided by the 20 meter lengths of track. So that would come out to be 0.60 meters. The track would expand by about 60 centimeters. Or you could do it another way. You could say, well, you could actually go back from scratch. Delta X equals the length, which is 10,000, multiplied by the thermal coefficient of expansion of the steel, which is 1.2 times 10 to the power of -5, multiplied by 10, comes out to be, hang on, have I got something wrong here? Let's have a quick look. What have I done wrong here? Well, let's work it out. I've got that, hang on. 10,000 meters multiplied by 1.2 meters. So that's actually incorrect, isn't it? That's mathematically incorrect. Have we got that right? Yeah. Okay. So I can spot that straight away because I worked it, because that 24 divided by 20 is not going to be a factor of 0.6. Now, if I then describe what may happen as a result of this, well, if the track expands by 1.2 meters and it's got nowhere to expand into, the track will buckle. It'll bend or it'll buckle. Or you could just say it will break. Okay, anything like that will probably do the trick. So that's the last of the written answer questions. The last part, so we've got just enough time to do this last part, is a multiple choice. Now we've got to be careful here. There are a lot of mistakes here caused by just misreading the question or not fully understanding the wording. So when you're deriving this formula, now tomorrow's lesson I'm going to go over the derivation of this formula because I don't think it's been that well learnt. So I'd like to go over that and help you with that. It says what's in it is an assumption. Remember, think about the 5 key assumptions. Yes, particles might collide with each other, but that's not what the assumption is. Well, the fact that particles are attracted to each other is just, that's we're in the assumptions. It says they're not. We know the motion of particles is random, and it does say so. So it's probably C. Relativistic effects can be ignored. Well, you can ignore relativistic effects, and you don't know about relativity, so it's probably not relevant anyway. So it's got to be C. Now, which term describes gas expansion or change in gas at a constant pressure? Baric, remember, the bar is a different unit of pressure. So iso means the same pressure. So it's A. Just to talk you through it, isothermic, thermic means temperature. So that's same temperature. Isochoric, remember, means same volume. It's one of the ones that's not quite so obvious. So an isochoric change is at the same volume, not the same pressure. Okay, and sorry was just my little joke. Okay, 27 degrees on the absolute temperature scale. Well, that's going to be 273 plus 27 gives you 300 Kelvin. There we are, easy peasy. Which quantity is described as, now the temperature energy required to raise the temperature of an object, not a unit mass, by 1 degree Kelvin. If it was the temperature required to measure the temperature of an object with unit mass, it would be the specific heat capacity. But for just an object, it's the heat capacity of the object. Okay, remember, you're familiar, most familiar with MC delta theta, but it's actually also equal to the heat capacity times by the change in temperature. So heat capacity is the mass times the specific heat capacity of the substance it's made of. Right, next one. How much work was done by an ideal gas during isochoric process? Isochoric, remember, means constant volume. So we know the work done is P times delta V. If it's an isochoric process, that delta V is 0, and anything multiplied by 0 is 0, so it's 0. When salt is added to ice, it causes the ice to melt. I'm just going to change my focus. There we are. It causes the ice to melt. What happens to the temperature of the salted ice as it melts? Well, if we think about it, it's going to require energy to break bonds. So that energy is going to come from somewhere. So it comes from the thermal energy of the ice. So the temperature of the ice will decrease as it melts due to the salt, because it's taking thermal energy away from the ice to actually cause the change in state. And that's the end of the basic walkthrough. Do you have any questions? Yeah, any questions? No? Okay, well, I'll stop just about there then. And what we'll do tomorrow is we will go through this, and we will look at the tomorrow. We'll look at the proof of PV is equal to 1/3 nm times the mean square speed of a particle of particles. Because I think it's one area I think that is not well known. You know how to use the formula, but there isn't a full understanding of what the formula actually is actually really telling you. Okay, so I'll see you all tomorrow. Please make sure you attend the lesson.